Okay, so hopefully you've actually watched the Forging the Elements video that I've also posted in our lecture slides, because that will help you understand the 3 different types of nuclear synthesis a little bit better. So we basically kind of described how all the different elements actually form, and once they form, they start forming into these clouds of gas, which we call nebulas. And these nebulas will slowly coalesce over time to form stars, planets, and things like this over time. So I just want to give you kind of a perspective of how large our galaxy is for a second. Now remember, ours is just one galaxy out of over about 300 million galaxies out there. So we're just a little small speck of that universe. Our galaxy is by itself is about 100,000 light years across, which means the star from one side of that galaxy to the other is going to take 100,000 years just to get from one end to the other. And at its thickest, it's about 2,000 light years thick. Okay, so it's estimated to be about 300 billion stars out there. Now, if you think about it here, our star is about a medium-sized star, and it has 9 planets around it, right? Okay, but only one of them is really habitable. So if you start thinking about the 300 billion stars that we have, and let's just say only half of them have planets around them, and only maybe half of those have planets around them that could be habitable. And if you start thinking about it, there's actually a really good probability that there is some kind of life out there within those stars. However, how easy would it for us to actually get to some of these people? Well, for us to get to our nearest star by the current rate of space travel that we already know of right now, and going as fast as we possibly could, it would take us about 28,000 years to get to that star. Okay, and so that's if we have along that star there actually is a planet that's actually habitable. So there's a lot of there's probably probability of us ever actually getting to another planet that is habitable is fairly low, and us talking to that planet also is fairly low, because if it takes 28,000 years to get to that location, it's going to be hard for us to actually communicate back and forth as well. So our Milky Way, our solar system is on the outer outskirts of our Milky Way, which is actually a good thing, because the vast majority of our stars are actually in the center of our Milky Way, where there's too much heat, too much gravitational pull for our Earth to actually, and life to actually form. But it's better that we're on that outer outskirts there. We have what we call the terrestrial planets, or rocky planets, and the gas planets. Now these formed because of the formation of our sun. Now here we have this big nebula. That nebula actually started to coalesce and forming into a disk, right? And so as that gas cloud contracts and starts spinning, it starts forming into these different small the gas starts to coalesce together into these balls of mass, like with our sun at the center and the different planets on the outside. Now the terrestrial planets were formed because as the sun's rays or a solar wind started blowing that material out, it blew the lighter materials like the hydrogen and the other gases out to what we call the jovial planets, whereas we kept kind of our rocky planets here with not much atmosphere. Okay, now if we have that material and it starts coalescing and starts forming into these balls of material or mass, the heavy stuff is going to go towards the center. So if you have this big ball of magma, think about all the dense stuff, how it's going to go to the center because of the gravitational pull. And then some of the densest stuff that we have should be iron materials. If you remember from our stellar nuclear synthesis, iron is one of the most common materials that's actually going to, and also densest materials that are going to go towards the center. And now also remember that that often our most radioactive material is also the densest material. And so things, if you look on the periodic table, the things that have are densest also tend to be radioactive because they're unstable. And so that's one of the reasons why we think that our center of our planet actually has a lot of iron to it. We'll talk a little bit more about that here. So if you look at the terrestrial planets that we have, you have Mercury here, Venus, Mars, and they all have things in common. They're all fairly small relative to the gas giants, but they also have some sort of atmosphere. Now Mercury's atmosphere is very thin. It's pretty much been blown away all and the planet itself is fairly small. And so all the internal heat's not very strong, plus the atmosphere has been blown away because of the strong winds, solar winds near the sun. Well, Venus, it's so volcanically active that there's always gases actually escaping from the planet itself, into the atmosphere itself, and keeps those gases within. So it has a very thick atmosphere, mostly of carbon dioxide and sulfur, things like that, things that are basically emitted from a volcanic eruption. And whereas Mars is about half the size of the Earth, and it's kind of died out slowly over time. Its internal heat's kind of died out, and therefore its atmosphere hasn't stayed around like we have here on Earth. Okay, so if you look at our Earth, there's really, we think it's layered, and one of the reasons we think it's layered, we actually calculated the average density of the planet to be about 5.5 grams per cubic centimeter. But the materials we see on the outside crust averages about 2.8 grams per cubic centimeter. It's basically quartz. We'll talk about quartz later, but the point comes, that's the average composition of our outside of our layers. It's the lighter material, or the silica, on the outside, whereas the denser material is in the center, which is what we think iron is, right? So if you take that average of the core being about 10 to 11 grams per cubic centimeters, and the continental crust, which is the top portion of the crust, on the outside of that there is being about 2.8. You can see that layering as the dense materials go to the center, the lighter materials go on the outside. Now as you go inward, you have more and more heat. Now this is one of the top missed questions in all of my exams. I have on every single one of my exams, and that's where the heat from our planet comes from. Most people say it comes from the core, and you're absolutely right, it comes from the core. But you're just describing where the heat is, not what's producing the heat. Okay, it's kind of like at your house. I'm saying that the heat comes from the furnace, and you're right on that. The heat does come from the furnace, but it's not what is actually, that's not where the heat's actually being formed. It's actually being formed from the burning of some fuel right in your furnace. And the same case with the heat in our planet. The core is where the vast majority of that dense material is, and that radioactive material is, and so therefore when radioactive decay occurs, it actually emits heat from that. And so the main heat source of in our planet is actually radioactive decay. It's not fission, fusion, friction from the rotation of the planet or anything like that. It's radioactive heat. Like I said, it's the number one missed question on most of my exams, and it's important to remember that heat comes from that radioactive decay. And the further down you go in the planet, the hotter it gets, because that's where you have the greater abundance of those dense radioactive materials, and also the more pressure it gets. We've tried to drill down into our mantle, into our core, but we haven't got that far, and that's because as we drill down into the Earth, it gets so hot that even the drill bit will start to melt, and the actual drill hole will start to slowly flow back inwards because of the heat and the pressure within the planet here. Now, the layering of our planet comes down to basically three basic layers, if you think about it based off of chemistry. Whereas the core is our nickel and our iron, which is that dense material within the core, the mantle, and then we have our crust. Now the crust is that less dense material, things like that we call felsic rocks or silicate rocks, with silica as being the number one material within that crust. And the core is mostly nickel and iron. Whereas the mantle is that gradation of things going from that silica all the way to the iron, right? So that layering is based off of chemistry. However, we also have a layering based off of what we call physical properties. So we have, for chemical properties, it's the core, mantle, crust. For physical properties, we call it, from the top to the bottom, we call it the lithosphere, the asthenosphere, the mesosphere, the outer core, and the inner core. Now the inner core is a solid ball of magma, not magma, sorry, of iron. Whereas the outer core is also iron and nickel. It still has the same chemical composition, but now it's liquid. Well, why would it be different? Why would one be solid and one be liquid? Well, it has to do with the pressure. And the pressure is so great that the inner core has to be a solid, whereas as it goes out, the pressure becomes less and less, and so now you can have a liquid core. Now that's important, that solid core, that liquid core of iron and nickel is important because that's what actually makes our electromagnetic field. That actually does our compasses, and basically protects us from that UV radiation that comes from the sun. Otherwise, we'd be getting high amounts of cancer and things like that, and life wouldn't really be able to exist on the planet. So it's very important and actually very nice that we have that. Now, the mesosphere is what we call the meso, meaning middle. That middle sphere, it is rigid, kind of like rock. It's kind of like ice. But ice, if you put enough pressure on it, can flow. So it still has that potential for flow, but it's kind of rigid, like ice might be rigid. Then the asthenosphere, astheno meaning weak, is that weak sphere or the plastic sphere on the top. Plastic, kind of like silly putty is plastic, right? Okay, or maybe molasses is plastic or something like that. It can move and bend a little bit. Whereas the upper portion, we call the lithosphere, litho meaning rock, is that rocky, cold outer crust on the outside. So the lithosphere, asthenosphere, mesosphere, outer core, and inner core is based off of physical properties, whereas the crust, mantle, and core is based off of chemical processes. Both of those names are important things you should know and to have an understanding of. Okay, so we know that the inner core is iron, not just because because iron was so prevalent in the supernovas and in our stellar explosions, but also because we have pieces of other planets or other materials as well. So we get meteorites that come into our planet. It's a lot like the different types of the core, mantle, and crust, right? Where some of the most common meteorites that we get is what we call stony meteorites, which are kind of characteristic of what we think the mantle might be, okay, and the crust. And then we have what we call iron meteorites, which would be more characteristic of what we have with what we call the core of our planet might be, which is mostly iron and nickel. Okay? Now, this is how we also got the date of our planet. The oldest rocks we found on our planet is actually some sedimentary rocks in the Jack Hills of Australia, which is dated about 4.4 billion years old. But we actually think the Earth is about 4.5 to 4.6 billion years old. And part of that is what we're actually dating is meteorites. When we see those meteorites and we date them, all of them come back to be about 4.5 to 4.6 billion years old, which basically ties it back to that formation of the solar system. When all that material was coalescing together, all of the planets were basically being formed at the same time, including our Earth. Okay, and so this is why we think that the solar system is about 4.5 to 4.6, and so is our planet about 4.5 to 4.6 years old. Okay, so I'm going to skip these other materials, so you can look at it in the slides if you want to in a little bit more detail. But just as a summary, the Earth's three main layers based on chemical composition is the crust, the mantle, and the core. And the 5 layers based off of physical properties is the lithosphere, the asthenosphere, mesosphere, outer core, and inner core. Now, this is very important in our discussion as we continue on talking about the rock cycle and plate tectonics, because this is where we get a lot of our heat from that movement of the materials of the crust, and then will form volcanoes, earthquakes, and things like that. But the asthenosphere is that plastic layer in which the crust or the lithosphere is moving over top of to allow the plates to actually move around. So these are all important concepts that we have in this last chapter here. And we'll talk about them more in detail as we go through it. We're not going to be talking about the whole formation of the planet like what we call the nebular theory, but we will be talking about the layering of the planets a little bit later on as well. Okay, this is it for this week's lectures. Please go do your quizzes and your homework, and and your discussions, so that we can actually get this week done, and then after that, prepare for next week. Talk to you guys later.